Welcome to some work problems from Chapter 7, which is called the central limit theorem. Now, we've looked at the uniform distribution and we've looked at the normal distribution. Both those have their applications. There are also other distributions totally different from those. They each have their own formulas and their own methods of attack. But what the central limit theorem tells us is there are certain calculations whereby you can use the normal distribution theory even if your underlying distribution is not normal. Okay, here are the two things that will always follow a normal distribution. One will be if you are taking a sample from a population. Now again, this population could be uniform or something else that's not normal. But if you take a sample and average the values, that average will follow a normal distribution. Now the nice thing about it is if you watch, say, the Chapter 6 videos, you know that once you get the hang of it, it's pretty easy doing calculations with the normal distribution. The other situation we'll find in this section is that if you take a sample and then add up all the values, that sum will also follow a normal distribution. So here's the problem we're going to look at. Suppose that the incubation time for an alien facehugger is uniformly distributed from 5 to 9 days. No, I didn't collect this data myself. First of all, let's define the random variable x. Okay, well, looks like we're looking at incubation time, so our random variable would be the duration of incubation times and it's given in days. Now this is a continuous distribution because it doesn't have to be 5, 6, 7, 8, or 9. It could be 5.29 days. You can measure it to any degree of accuracy. Next, give the distribution of x. Well, you know, we were told that it's uniform. Okay, so x would be, we use uniform, U for uniform, and be uniform from 5 to 9. And C and D are just review problems, okay? But I had my reasons for putting them in here. Find the mean of the distribution x. Well, recall that the formula is a plus b over 2. 5 plus 9 over 2. That would equal 7. So the mean would be 7 days. No surprise there, right? In fact, you really didn't need to do the math. 7's right in the middle of 5 and 9. And the standard deviation, the formula is b minus a. That would be 9 minus 5 squared over 12, the square root of that. Obviously, you wouldn't do this one in your head. To 2 decimal places, I got that the standard deviation was 1.15 days. Now, before I advance the slide, the thing I want make obvious to you is this is not a normal distribution. Incubation time is uniform, not normal. Okay? Now, to that information that I gave you a moment ago, at the top of the page, let's add this. Let's suppose we study 20 randomly chosen facehuggers, and we're interested in the average length of incubation in this sample. Average is a mean. The random variable x bar would be the average length of the incubation in days. Look, there are other ways you could write this in English. I mean, I could have just said the average incubation time or something like that in days. All right, now give the distribution of x bar. So I pointed out to you in the previous slide, the incubation time is not a normal distribution. It's a uniform distribution. But the nice thing is if you take a sample from any distribution at all, the sampling, essentially the distribution of that sample, will be a normal distribution with certain adaptations. The distribution of x bar will be as follows, and you should have seen this in previous reading or viewing of videos. It is normal, and the mean will be the mean of that original distribution, so in our case it would be 7 days. What it changes is the standard deviation. It will be the standard deviation given on the previous slide, but it will be divided by the square root of n. So before you reach for a calculator, in other words, you'd have to do that calculation, that standard deviation divided by the square root of n. So in part G, let's find the probability that the average length of incubation for our sample is less than or equal to 8 days. Okay, so we will have our normal curve here with, now I'll just remind you that the mean, which we found on the previous page, was 7. And so here's what we have to find. The probability that x is, talking about 8 here, less than or equal to 8 days. Doesn't really matter if it's less than or equal to in a distribution like this. You're going to get the same value. So here's what we have to find. Okay, so this, of course, is going to be another calculator problem, but let's keep in mind what parameters we're going to use. So let me just come up to here. Again, that mean was 7, and if you take the standard deviation from the previous page, it was 1.15, and we'd have to divide by the square root of what? What is n? Our sample size, 20. Okay? Oh, by the way, here, I already put this in a calculator, so let me just tell you a couple decimal places what I got for that. That turned out to be 0.26. Okay, so you'll be able to easily plug this into your calculator to get that answer. The main thing you had to do was you couldn't use the standard deviation from the previous page of 1.15. You just had to remember it's a sample size of 20, so you had to divide by the square root of 20. Okay, here this video is going to be very short, so I'll go and plug this into the calculator, perhaps especially for those of you who maybe haven't seen me do this before. So I do second, I do distribution. I want the second one there, normal, CDF. So I want to find a probability. Now on the picture, I better go back just for a second. On this picture, the right-hand value shaded there is 8. What would be the left-hand value? Well, you might think it's negative infinity, but actually, can we have a negative value for the incubation time? No, of course, from a practical point of view, the left hand would be 0 days. So the lower for this problem would actually be 0. Now, if you we're thinking negative infinity, it's going to make hardly any difference for the answer. The right-hand one was 8 days. Our mean, we saw, of course, was 7 days. And our standard deviation that we have to work with is the 0.26. All right. And what are we going to get for that? to 4 decimal places, 0.9993. So, in other words, we can assume that it's almost certain. I think it had 0.9999, then a 3 in the next one, so it's almost certain that the incubation time will be less than 8 days. That's because the standard deviation here was pretty small. It was only 0.26. All right, I just have one more problem I would like to work with you in this section. It'll be for a sum. So again, incubation time uniformly distributed 5 to 9 days. It's not a normal distribution, it's uniform. We saw previously that if you take a sample, the mean can be calculated by the normal distribution, and so can the sum of all the days. So the random variable here, sum of the x's, defining that in words, it would be the sum of the 20 incubation times, for our particular sample. Now, to give the distribution, if you've read the book, you know that it's not just the mean and the standard deviation we previously figured out. The distribution for a sum, it'll be normally distributed. But now for the mean, here's what I want you to remember. Remember how the mean was 7? It was the number between 5 and 9. Well, if the mean is 7 days apiece on average, but you have 20 of those and you're adding up all those, it'd be 7 times 20, wouldn't it? So the formula for it is n times the mean. 7 times 20 would be 140. And then for the standard deviation, you take your original standard deviation, which was 1.15, and what you do is you take that and you multiply it times the square root of n. So 1.15 times the square root of 20. What I got for that was to two decimal places was 5.14. And now we'll be to answer this question then using the normal distribution theory. Let's draw our picture. So now the mean is 140. What's the probability that this sum will exceed 130? So we'd have 130 right here. Exceed 130, so we'd be looking for this area here. Now look, before we even do the calculator, the answer is going to be a pretty large number, isn't it? Because most of the curve there is shaded. Let's do the calculation to finish off the problem. Oops, did maybe more than I wanted there. Okay, so let's pull up our number 2, our normal distribution. And let's see, the lower, we just drew it, was 130. Theoretically, there's no bound on the upper, so I'd do scientific notation to put in a large number. I want the EE button here, so I did second, and then I just will type in 99, and this means 10 to the 99th power. Let's see, our mean, now we're not going back to the original mean, we're doing to the one we just calculated. That mean is 140, and the standard deviation that we just calculated was, sorry, I suddenly lost my place. Oh, it's 5.14. 5.14. All right, let's get the answer. Turns out to be to 4 places 0.9741. We knew it would be big because most of the area was shaded. Okay, this video may be a couple minutes less than the last one. Good luck, folks.